Okay, chapter 4, section 1. We're going to look at exponential functions, graphs of exponential functions, and then compound interest. All right, so here we're going to study exponential functions. Exponential functions are functions where we have a base number raised to a power where the variable, independent variable, is in the exponent, right? So here is a prime example, classic example is 2 to the x power. And that very quickly gets, or very often gets confused with x to the second power, right? So here, the independent variable, the input value, is in the exponent to the power of x, compared to here, where the base number is the independent variable and it's being squared. So let's compare these two guys in a table setting so you can see how they differ a little bit. What should we use? Let's see if we can use. Okay, so we want to compare x to the second power here and compare it to, let's put it over here, 2 raised to the power of x. So we create a table, right? So this is going to be the x value here. So for example, when x is 1, I'll have the input value raised to the power of 2, 1. Let's try a different one. How about 2? That works. 3. Okay. So it's being squared. And then over here, let's let this be equal to 2 raised to the power of this value there. Good. So 2 to the power of 3 equals to 8. All right, so let's make this a little bit larger. About 20. All right, so let's see how this grows. Let's make this equal to this one plus 1. This. Okay, so 3 squared is 9, 4 squared is 16, and now 2 to the power of 3 is 8, and 2 to the power of 4 is 16, so that's how that goes so far. And let's see what happens as this expands a little. So as we grow past that a few values, see how this grows? Let's expand this, it's running out of space. At first it looks like they're both about the same. 3 squared is 9, 2 to the third power is 8, 4 squared is 16, and 2 to the power of 4 is also 16. But then, pretty quickly, the 2 begins to grow much, much faster. See how these values are still relatively small compared to that? Even at 10, 10 squared is 100, and 2 to the 10th power is already 1024. Okay. And then so on and so forth. We go over down to 15. 15 squared is 225. 2 to the power of 15 is already 32,768. Right? It's moving down here. Let's go to about something like 50. What's going to happen when we get to the 50? At 50, this thing is already out of control big. It's already just using scientific notation to approximate this, so let's just stick to this one. Even at 36, 36 squared is only 1,296, but 2 to the power of 36 is already in the billions. Is that 68,792,000,000? Oh wait, is that trillion then? I can't tell. Commas. That makes it easier. Spaces. Okay, so that's going to be millions. Yeah, 68,719,478,736. So in order of magnitude, close to 69 billion compared to 1,296. Right. So clearly, 2 to the power of x grows much, much faster than x squared. Right. Even though they begin life innocently enough, look similar. 2 to the x power will grow much faster. So that's true for any of the exponential numbers. Exponentials grow much faster with any base than with any base bigger than 1 than its counterpart, where we have the variable raised to that same power. Good. Questions? 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 No? Okay. That's all we really want to get out of that. So don't confuse those. Okay. So to study exponential functions, we must first kind of define what it means for it to be some value that has a form a to the x power. When x is a real number, for x being any real number, when x is a natural number, like we just saw, a 2, x to the second power, when we see a counting number or a natural number in the exponent, we can kind of visualize what that means. So we know that 3 to the 4th power means that we're going to have this be multiplied by itself 1, 2, 3, 4 times. And if we have a fractional power, like we saw that this meant that, so if we have 3 raised to the 5 seconds, it's the same thing as 3 to the 5 seconds raised to the 5th power, which means that this is going to be root 3 times root 3 times root 3 times root 3, 1, 2, 3, 4, 5 times. It's one way of visualizing it. But how do we get an actual number out of this thing, other than using technology and getting a value from there? Well, what we want to think about is approximating it so that it gets close to a rational value. Good. So if we want to figure out what is 5 to the power of root 3, right? How do we put an irrational number in the exponent? What does this mean? 5 multiplied by itself root 3 times? That doesn't seem to make sense, right? Or 2 multiplied by itself pi times, right? Again, that doesn't quite make sense. So what we're going to do is just approximate this answer by looking at what happens as we get close to that answer, right? As we get closer and closer and closer to a value of the exponent, we'll get closer and closer to a good approximation. So root 3, for example, is approximately this. So if we want to find out what is 5 to the root 3 power, we're going to think about, well, first of all, what is 5 to the 1st power? Okay, that gives us a solid answer. Not exactly that one. Okay, but let's think about what is 5 to the 1.7. 5 to the 1.7, well, that's a rational number. That's 5 to the power of 17 over 10. Oops. 5 to the power of 17 tenths. And we know when we have a fractional one, then we can restore it, right? We know how to approximate it this way. So I can tell that. Okay, still not the right answer though. Okay, but then let's figure out, well, what is 5 to the power of 1.73? That's another fractional one, right? As long as it terminates, then I can rewrite it as a fraction. It might be a really ugly fraction. This is 5 to the 173 over 100. But it's nonetheless a fraction, a rational fraction. Okay, so we keep going, and eventually we'll see that there's a pattern as these begin to approach the real answer we're looking for. Okay, does that make sense? Any questions? Good, good. So when we want to find what is 5 to the power of root 3, we can approximate it by doing 5 to the power of 1.732. If you want to get an even better approximation, well then approximate it by going out to more decimal places here. Maybe approximate root 3 to 4 decimal places, or 5 or 6, and then that'll give you a pretty good approximation. Good, 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 good. Okay, so there is more sophisticated math out there that can help us mathematically confirm that this process works, but we don't really want to take that side tour and go into that rabbit hole about how to prove that this is true. I think intuitively it makes sense, so this is good enough. But let's try it with pi just to make sure. So the question is, what would be 2 to the pi power? How do we figure out what that is? Right? This is 2 multiplied pi times? Like what? What does that mean? All right, it's 2 times 2. It's supposed to be, uh-oh, it's going to give me trouble. 2 times 2 times 2 times 2, right? And then this thing multiplied by itself, pi times. This kind of definition just doesn't really make sense. Like, what the heck does that mean? This works when we had 2 to the 7th power, right? That was 2 times 2 times 2 times 2 times 2 times 2, 1, 2, 3, 4, 5, 6, 7. But it doesn't work with pi, right? Okay, so what do we do? Okay, so pi is approximately 3.141592654. That's about as much as I know. Do you guys know there's like contests for people that memorize digits of pi? The winner is like way out there. You should Google it. The most number of digits memorized. It's in like the thousands. People memorize thousands of digits and they win the contest. It's crazy. Anyway, all right, so we know that pi is approximately this. So when we want to find out what is 2 to the pi, well, we begin by something really simple. How about 2 to the third power? I know what that is, okay? And then that's not good enough, though. All right, I want a better approximation. How about 2 to the power of 3.1? We can figure out what that is, right? That's a rational thing. I can rewrite that as 31 over 10, and then I have an answer to that. I know what that can be. And then I can approximate it even more by doing 3.14. And then I can approximate it even more by doing 3.141. And so on and so forth, right? I can just keep going and get as much accuracy as I want, depending on how far out I go. And eventually you'll see that these outputs begin to approximate, begin to get closer and closer to some output, and then you'll be able to get a really good guess at what this approaches. Does that make sense? Okay, like I said, there's some nice sophisticated math to confirm that this process works, but we're not going to go down that hole. But what we want to get out of this is just to know that we can always find the answer to any base number raised to any exponent, and that exponent is allowed to be any real number. Okay. All right, so a definition of an exponential function is going to be something of the form f of x equals to a to the power of x, where x is our independent variable, x is allowed to be any real number, and a is also any real number that is positive. We're only going to be focused on the positive end of things, and also not zero. And it's not zero just because then that would be a really boring answer. 0 raised to any power is still 0, so the answer is just 0. Likewise, it's also not allowed to be a positive 1, again, because it's kind of a boring answer. 1 raised to the power of anything is 1, so there's really nothing special happening there. So we really just ignore the cases of a equals to 0 and a equals to positive 1, and focus on all the other positive numbers. Good. So that's our definition for an exponential function. So let's explore some of these things. What does it look like when we have 2 to the power of x, 3 to the power of x, 10 to the power of x? How do we graph them? What do the graphs look like, right? So whenever you begin exploration on something new, you should just think about starting off from basics. What happens when we have a nice little table, and what kind of values do we get? So if we just have 0, for example, this would just be 2 to the 0 power, which is 1. 1 would be 2 to the 1 power, which is 2. 2 would be 2 to the second power, which is 4. Okay, so we begin to see a pattern. Now, with the negatives, it gets a little interesting. We get 2 to the negative 1, and remember that when we have a negative in the exponent, to get rid of that negative, we flip it underneath 1. So 2 to the negative 1 power is the same thing as positive 1/2. 2 to the negative 2 power is equal to 1 over 2 to the positive 2 equals to 1/4. Good. Notice that the outputs are never negative, right? Because if we input a positive number, we're raising it to a positive exponent, we're going to get a positive number. If we're raising it to a negative exponent, then to get rid of that negative in the exponent, we flip it underneath 1, and we still get a positive answer. So there's no such thing as a negative output from this function. Good. Same thing with these other ones. Let's do a couple of values. If we have 3 to the x power, and we have x here, then when x is 0, 3 to the 0 power equals 1 still. 3 to the 1 power equals to 3. 3 to the second power equals 9, and so on and so forth. Negative 1, that'd be 3 to the negative 1 power equals to 1/3. And negative 2, that would be 3 to the negative 2 power equals to 1/9. Right, going that way, so forth. And similar with base 10. Questions? Okay, let's evaluate some of these things using technology, it says. All right, well, using technology. So for part A, we have f of 5. So the f function is this, must be 3 to the 5th power. So we can use technology to figure out what that is. For part B, well, I guess I can just put it on here. What's this? So this one is going to be 3 to the 5th power. This one is just going to be 3 to the pi power. This one is just going to be 3 to the root 2 power. And this one is going to be 3 to the negative 2/3 power. So really we just want to practice or make sure you know how to use your calculator to find these answers. Let's use our calculator to find these answers. Okay, so let's get our calculator out. Wherever you start off in your calculator, you can hit this button, quit, quit, to go back to the main screen, hit clear. And so 3 to the power of, this little caret symbol up here is the power, to the power of. Now in my calculator, it does this little thing where it goes up to the exponent and has a little box, and then I can type in the 5 up there. So it's sort of the newer user interface. But a lot of the older calculators are going to have this little caret symbol that appears there, this symbol. So if yours works that way, just know that when you see that little caret symbol, it means that you're raising it to that power. Okay, so next, how about 3 to the power of pi? To the power of pi, and pi is right above the caret symbol, so hit second, and then that caret symbol, and then enter. I get that. 3 to the power of, and then I would wrap it in parentheses. We have -2 divided by 3, close the parentheses. Let me get that. And then 3 to the power of, parentheses, and now we have the square root of 2. We can use this little square root number value right in here. So square root of 2, close parentheses. Go out here, close parentheses. So delete this guy, like that. And close parentheses. Enter. Okay, and yeah, okay, so here, this little caret symbol, this is how the little exponent will appear for a lot of you guys when you type it in. So just making sure people know how to use your calculator. Anybody have any problems with their calculator right now? Typing these guys in? No? Okay, graphs of exponential functions. So, let's look at these two functions. Let's try and graph them and see how they're related to each other. In order to graph anything, we begin with a table. So again, I'm going to start off with the table of x and 3 to the x power and do some values there. How about evaluate it at 0, at 1, at 2, at 3, dot, 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 -1, -2, something like that. As we saw before, this one represents 3 to the 0 power, which is 1, 3 to the first power, which is 3, 3 to the second power, 3 to the second power, which is 9, 3 to the third power, which is 27, and so on and so forth. 3 to the -1 power equals to 1/3, and 3 to the -2 power, I'm going to give you trouble, 2 power, which is equal to 1/9. Good. Okay, so we have all these ordered pairs from here. We have, just when I thought I wasn't going to have trouble anymore, -2, 1/9, -1, 1/3, 0, 1, 1, 3, 2, 9, and 3, 27. Good. All right, how does that compare to the other function? We have this other function. Let's create a table over here. X, and then we have 1/3 raised to the power of x. So 0 is easy because anything raised to the power of 0 is still going to be a 1. 1 is easy because 1/3 raised to the power of 1 is going to be 1/3. Negative, oops, not negative, +2, also easy because we have 1/3 squared, which will be equal to 1/9. The other direction, -1, I have 1/3 raised, and then one fraction divided by another fraction. We simplify this by multiplying the numerator times the reciprocal of the denominator. This thing just turns into 3 to the power of 1, just 3. Good. -2, then we have 1/3 raised to the -2 power, which then turns into 3. You can also do this. This 1/3 is the same thing as 3 to the -1 power raised to the -2 power. Right? Let me put that in color. This part in here, and this part in here. Color. 1/3 can also be written as 3 to the -1 power. And now when we multiply the exponents, we end up with 3 squared, which is equal to 9. Good? Any questions? No? 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 Okay. So notice the relationship between these two. as the input goes bigger and bigger and bigger and bigger, as x goes to infinity for this function, the outputs, y, are heading toward infinity too. They're growing out of control. As x goes toward negative infinity in this function, the outputs are going to be getting smaller and smaller and smaller, right? 1/3, 1/9, the next one will be 1/27, 1/81. So these things are growing toward 0. And they're getting smaller and smaller and smaller. The opposite is true here. As the input gets bigger and bigger and bigger and bigger and bigger, as x approaches to positive infinity for this function, the outputs are getting smaller and smaller and smaller. The outputs here are heading toward 0. Whereas over here, as the inputs are heading toward negative infinity, right, because we have a fraction 1/3 raised to a negative exponent, then this thing is heading toward positive infinity. Good? Questions, comments? All right, so let's look at the graphs. So before we know how to graph anything, then we'll just start off with graphing a bunch of ordered pairs. Let's create a table. I need you to frequency. Let's put you there. And let's use 3 to the power of x. All right, so 0, it leads to 1. 3 to the 0 power is 1, so that's this dot right there. Okay, then when I put a 1 in there, I get 1 comma 3. 3 to the 1 power is 3. And then when I put a 2 in there, I'm already jumping to 9, which is way over there. So I'm trying to get these 3 dots. I can also do -1. -1 leads to 1/3, which is 0.33333. That's this dot. -2 leads to 1/9, which is 0.111111. That's this point. -3 leads to this 1/27, which is 0.033. Okay, so you see it's getting really, really small fairly quickly too. Okay, so we start to see a shape. Luckily, since we have technology, we don't have to stick to just counting numbers, natural or integer values. We can find some decimal values to fill in this graph. So how about 0.2, 0.4, 0.6, 0.8, 1.2, 1.4, 1.6, 1.8, right? How about some other values over here? How about -0.2 and -0.4 and -0.8? Okay, so you start to see what the shape looks like. It's going to have this sort of a shape. Good, so then we can just jump to the calculator graphing it. And let's make it green. Okay, so if I keep going and I find an infinite number of dots here, every possible input value that's in the real number line, then I will get an infinite number of ordered pairs when I graph them, and all those ordered pairs will eventually begin to look like this smooth curvature, which is really an infinite number of ordered pairs that satisfy this equation. Okay, so this is the graph of 3 to the x power. Any questions? No? Okay, so we can do the same thing with 1/3. Let's go over here, let's get a table going. Axis 1. Parentheses 1 divided by 3. Oops. To the power of x. Okay, so 0 still leads to 1. Let's make it a different color. Let's make it orange. So 0, 1 is still a value. 1/3 to the 0 power is still 1. And then when we put a positive 1, then we get a 1/3. When we put a 2, then we get a 1/9. When we get a 3, then we get a 1/27. So that's these values right here. Right? This is 1/3 raised to the 3rd power is 1/27, which gives you this decimal. 1/3 raised to the 2nd power is 1/9. 1/9 is 0.1111. And this is when we put in a 1. 1/3 to the 1 power is 1/3 is 0.3333. And here's 0.1. Okay, so you can see it's getting smaller and smaller and smaller. As the input values go toward positive infinity, the outputs of this function are getting smaller and smaller and smaller. Okay, in the other direction, if we type in a -1, we get a +3. If we type in a -2, we get a +9 up here. Good. And again, just like before, we don't have to stick to whole numbers since we have a nice computer to help us. We can fill in the blanks with some decimal values. How about 0.2, 0.4, 0.6, 0.8, 1.2, 1.4. Okay. How about some negative values? How about 0.2, negative 0.4, negative 0.6, negative 0.8, negative 1.2, negative 1.4, negative 1.6. Okay, so I start to get a bunch of ordered pairs, and it doesn't take long to hopefully convince you that if I kept going, I found an infinite number of those dots, eventually that graph will look like this. 1 divided by 3, close parentheses, the power of x. Looks like that, and let's put it in orange. Here's orange. There we go. So if I kept going and I found an infinite number of dots, every possible input value that's a real number, plugged it into this little thing, eventually all those ordered pairs will give me this orange shape here, this orange curvature. So eventually get rid of the individual dots and go, okay, this curvature is the graph of this equation. And notice how it relates to the graph of 3 to the x power, right? The green one is 3 to the x power. The blue one, the orange one is, let's get rid of that. Let's get rid of that. So the green one is 3 to the x power. The orange one is 1/3 to the x power. Good. Questions, 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 questions? That can also be seen if we kind of play around with the equations themselves, since we know all about transformations from a prior section. Let's make a little space here. Since we know all about transformations from the prior section, we know that if we have f of x equal to 3 to the x power, and then we have g of x equal to 1/3 to the x power. As we said, 1/3 can be rewritten as 3 to the negative 1 power raised to the x, which is equal to 3 to the negative x power. So that's just this function evaluated at negative 1, f of negative x. Right? If I took this function right here and I plugged in a negative x, I would get 3 to the negative x. So these two are related this way, and we know from before that this is a reflection about the y-axis. F of x reflected about the y-axis. Any questions? Good, kind of, sort of, kind of. Okay, so here's a table of the same things we did. We put in some input values. We raised 3 to the power of those input values. We got some ordered pairs from those. If we graph them, we will slowly be able to create this red one. We also did 1/3 of the x power, tried some values, get some outputs. If we graph them, eventually we get that. And we see that they are a reflection about the y-axis of each other. Good, which we can do right here. Confirm that they're a reflection about the y-axis. If we do it for multiple values, we can see that this is true. Right? So let's use Desmos to kind of isolate what this means. So we had 1/3 and 3. We can also have y equals to 2 to the power of x. And of course, it's going to look like that. And if we have y equals to 1/2, oops, 1 divided by 2, the power of x, it's going to look like that, right? So they're always a reflection about the y-axis. Whenever the base number is a number bigger than 1, it's going to have this sort of general shape, always. It's going to go through the point 0, 1, no matter what, because no matter what the base is, raised to the 0 power, we'll always get 1. But as that base number gets bigger and bigger and bigger, like maybe that becomes a 5, maybe that becomes an 8, maybe that becomes a 13, right? As that base number gets bigger and bigger and bigger, then it grows toward infinity faster in this direction, and then over on this direction, it grows towards 0 faster, right? That's what happens as the base number gets bigger and bigger and bigger. And then all we have to do to find its mirror image is to turn it like that. So now that's a perfect reflection about the y-axis, these two. Good? Questions, questions, questions? So we can have a slider situation here about equals to a to the power of x, where a is a slider. So if a is a value that's bigger than 1, like this, it grows and grows and grows and grows and grows and grows. See how it always has that same general shape? It just gets steeper and steeper and steeper the bigger that base number is, like this. And then when we get to 1, the output is silly, because 1 raised the power of x is always 1. So 1 is just a flat horizontal line, right? 1 to the x power is just 1, so it's just the line y equals to 1. And when we get to a decimal value between, let's put 0.01, and let's make this 10, 5.1s. So then as we go to decimal values between 0 and 1, then this thing begins to flip in the other direction and have a shape that looks like this. Right? So it looks like this, and then it flips the other way. And it looks like this, and then it flips that way. Any questions at all? So this way means that the base is bigger than 1. This way means that the base is between 0 and 1, not negative, right? We're not allowing the base number to be a negative number because that has the potential of having irrational numbers and weird things that could happen. Imaginary numbers, I should say. Questions? Good. So it's kind of hard to spot here, but this yellow one and this purple one are reflections about the y-axis. The purple one is 10 to the x, and this yellow one is 1 over 10 to the x power. Notice that they all go through the point 0, 1. This blue one is 1/5 to the x power, and then over here in this blue, we also have 5 to the x power. Wait, how come? That's weird. In some cases, they left the colors. Anyway, their color scheme's a little weird. Any questions? No? Sort of? Kind of? Sort of? Kind of? Right? So when the base number is bigger than 1, the graphs will have this sort of a shape. And as x goes toward infinity, the outputs will go toward positive infinity. And as x goes toward negative infinity, the outputs will go toward 0. Right? That's when the base is bigger than 1. When the base is between 0 and 1, it's a reflection about the y-axis, and then the opposite happens. As x goes toward positive infinity, the outputs go toward 0. As x goes toward negative infinity, the outputs go toward positive infinity. But notice that they all go to the point 0, 1, and also notice that there's never a negative output. The outputs are always positive no matter what. Good. So we generalize that in this kind of table, right? Whenever the base is bigger than 1, this is the general shape of the exponential graph, always. We just have to figure out just how steep this goes. The bigger the base, the steeper it'll go, the faster it'll grow toward infinity, the faster it'll grow toward 0. And when the base is a value between 0 and 1, then it has this sort of a shape. Right? No, it still goes through 0 and 1. It's just a matter of determining how steep that curvature is. Questions, 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 questions? No, no, no? Okay, so let's say, for example, we want to define the exponential functions of the form a to the x power to these guys. So this was all that's given. Well, from here we can tell that whatever this is, it must be something of this form. And we can tell that f of 2 leads to 25. So that means that some number being squared equals 25. We can take the square root of both sides and see that this is plus or minus root 25. Which means that this is equal to plus or minus 5. But in exponents, we never allow this to be negative, so we ignore the negative. Ignore the negative. And so we get to conclude that this must be the exponential function f of x is 5 to the x power. Right? And confirm that when we put a 2 there, it works out. Good. On the other hand over here, that must mean that f of x equals to a to the x power. And we have that f of 3 led me to 1/8. Good. So it must mean that a to the power of 3, some number raised to the power of 3 must be 1/8. We can raise both sides to the power of 1/3. Which means that a must be equal to 1/2. A must be 1/2. So we have f of x equals to 1/2 raised to the power of x as our function for this guy. And this is the function for that guy. Any questions? So I'm having some computer issues here. Skipped a bunch of things. 24, 25. Okay, so this is the work we found already. Solutions for that. Compare the rate growth of these two functions. I already did a little bit of that to show how much faster this grows when compared to that. So don't confuse them. All right, compound interest. So I'm gonna try and develop the formula for it. That's the goal here. So what I'm about to do is overly complicated. Don't worry, this is not what you're expected to do on a regular basis. I'm gonna use this example to develop the formula we need, and once we develop that formula, it's a pretty easy formula to use. So let's say that we have a case where we want to invest money, and it's like a real simple situation where we begin with our starting balance. Oops. Starting balance is over here. And I think I did 5,000 last time, so let's just stick to it. So some of this will be review, like I said. So let's say I started out with $5,000 to invest, and after a set period of time, and the period of time is usually 1 year. It's the most common kind of thing, and that's because interest rates are usually given in terms of a year. So let's say that the investment is paying off at a rate of interest rate is 5% annual. And that so it's annual interest rate, and so we'll have time over here. All right, so interest rate, interest earned is going to be the next column here. Interest earned. So we're going to go in, since this is given in terms of a year, we're going to go in annual intervals. So interest earned after 1 year. In 1 year. Okay, so here we're going to go with year number. I'm not happy. Okay, so year number 1. And I'm going to put that in color since I want that to kind of pop out after 1 year. Okay, so, well, anyway, okay, so interest earned. So interest earned is just going to be the 5% that you get on the 5,000. Okay, so it's just going to be a formula of 0.05 times 5,000. So 10% is 500, half of that is 250. So you're going to make $250 the first time. All right, so at the end of the year, you're going to have your original balance plus the interest you just earned. However, instead of, so it's going to be $5,250, right? However, let's say I want to write it this way. So I want to write it as the 5,000, say end balance, end of year balance. So it's going to be the 5,000 plus the $250. So I know it's going to be 5,250. But instead of writing it this way, I want to write it in the following way. This $250 came as a result of multiplying these two things together. So I'm going to replace it with 5,000 times 5,000 times 0.05. Right? That's what this is. Plus 5,000. 5,000 plus, and then a multiplication of these two numbers. That gives me that interest earned. And now what I want to do is I want to factor out the 5,000. Put it out here. 5,000 times 1 plus 0.05. Okay, so then if I add these two things together, it gives me 5,000 times 1.05. Okay. So then if we multiply those together, if we get a calculator and multiply these together, you'll see that you get the exact same number, 5,250. So 5,000 times 1.05 is 5,250. Good. Okay. It sort of makes sense if you think of it in terms of percentage, right? Note that 1.05, when we converted it into a percentage notation, right, we moved 2 decimal places, that's 105%. Yeah, you started off with 100% of your money. You got 5% annual interest. So at the end of 1 year, you get 105% of your money. Right? You can think of it that way. Good. Okay, so then we're off to year 2. The initial balance at the beginning of year 2 is now $5,250. $5,250. But as we just said, another way of saying $5,250 is to say 5,000 times 1.05. Okay, we'll keep that in mind for a second, but anyway, it's this amount. So at the end of this new year, you're going to also earn interest. And the fact that you're going to earn interest not just on your initial investment, but now you're going to earn interest on the interest you earned at the end of the first year, right? That's the part that's called compound interest. The fact that the money you made in interest from the first year is also going to earn interest on its own. The money you make makes money. Money makes money. It takes money to make money, right? That's how rich people stay rich, man. They have a bunch of money, and then their money makes money, so they just gotta kick back and watch their money grow. All right, so let's multiply these two things together. And what do we get? 0.05 times 5,250. That's going to be $262.50. And notice, of course, that you're making a little bit more money. The previous year, you only made $250, but this year you're making $262.50, right? An extra $12.50. That doesn't seem like much, no big deal. But what if these were in terms of millions, right? You have $5 billion, which means that you earned $250 million in interest, just leaving it alone, not doing anything. And then your earned interest, so the following year you made an additional $12 million, right? For nothing special, you're just getting richer, an extra $12 million the following year. And the following year after that, you're gonna make even more money, right? You're slowly making more and more and more and more without really doing anything, right? You're just letting your interest work for you. Okay, all right, so moving on then. So now at the end of your second year, you're gonna have your initial balance, which was this $5,250, plus your new interest, which is $262.50. So we can just add those two things together, and of course you're going to have $5,512.50. Good. Okay, so that should be the balance at the end. Oops. Wait, what did I do? This is wrong. This is 5,200. Why did I put 55,000? 10,512. $10,512.50. Okay, so that's a perfectly good balance. But again, we're gonna try and see a pattern. And to do that, I'm gonna make some replacements. We said from before that another way of saying 5,250 is to say that it's this little multiplication, right? This multiplication is that initial balance, right? We got that from the line right above. So I'm going to replace this 5,250 with 5,000 times 1.05, okay? Plus, and now this 5,262 was the multiplication of these two numbers. So that one should be 5,250 times 0.05. That's what gives me this number here. Right? And what we just said that 5,250 is the same as this one. So I'm going to repeat it one more time and say that this is 5,000 times 1.05. And like I said, this is getting really tedious. Remember that this is just so we can develop our formula, and then once we develop our formula, we never have to do this again. So you're not going to be expected to be repeating this on your own. I just want you to understand where that formula comes from. Okay, so this I just copied down. Here, the 5,250, I replaced it with 5,000 times 1.05. And then once again, we can see that we can factor these two. This is identical to this, so we can factor it out. Put it out here on the outside of the parenthesis, 5,000 times 1.05. And then on the inside, we have this plus this, right? Blank plus blank is going to be on the inside once we factor that out. Factoring out 5,000 times 1.05, we end up with a 1 here. And then for the second term, the only thing that remains is 0.05, right? Which can be combined again, and we end up with 5,000 times 1.05 times 1.05. And they're identical, so of course we can rewrite them as 5,000 times 1.05 to the power of 2. Okay, so at the end of the second year term, your new balance is going to be $10,512.50, or expressed this way, it's going to be equal to 5,000 times 1.05 to the power of 2, which leads to the exact same number, 10,512.50. Right? So they both give you the same value. And at this point, we can start to see the pattern. Here we had 1 at the end of 1 year, and here we have this pattern. I'm going to put a 1 right there so we can see it. It's the initial investment times this number, and this number is 1 plus the interest rate, raised to the power of 1 because it's 1 year. At the end of 2 years, it's going to be 5,000 times 1 plus the interest rate, 1.05, to the power of, and then this guy is going to be a 2 there, right, because it's the end of the second year. So from here, we can pretty easily guess what's going to happen at the end of the third year. If I told you, hey, figure out what happens at the end of 3 years, what's the balance on the account going to be? At the end of 3 years, it should be 5,000, the initial investment, going back to square one, the initial investment, times 1.05 raised to the power of 3. Right? At the end of year 3 over here. The initial balance on year 3, I know is going to be $10,512. Wait, what did I do? Did I do something wrong here? Ah, this is wrong. And nobody said anything, man. I need coffee. So, $5,250 plus the interest earned is only $262. This should be 5,000. I don't know what I was thinking. 5,000. $5,512.50. I can't believe you guys didn't say anything. Just let me go on and on and on. Okay, so then that part's right. That part's right. And then, of course, that means that the product of these two equals this number. Man, that'd be great interest if it jumped from 5,000 to 10,000 in 1 year. It's a little too aggressive. So this thing then should be $5,512.50. Okay, are we good now? Any questions? Any questions? Any questions? Good. Okay, so the starting balance at the end of the third year is $5,512.50. And I know you're going to earn some interest, and that interest is going to be 0.05 times $5,512.50. So it's going to be 0.05 times $5,512.50. So you earn $275 with 60, let's round it up to 63 cents, 63 pennies. Good. And then you add these two together to give you your result. And I could add these two together, or I can apply this formula. So when I apply it, it'll be 1.05 to the power of 3 times 5,000. Let's just use our calculator on here. So launch, we'll use it in a minute anyway. Okay, so it's 1.05 to the power of 3. Enter. That's my answer when I have the 1.05 to the power of 3. And then that previous answer times 5,000 gets me to that. $5,788.25. Any questions? That's what we get here. $5,788.13. Rounding. Good, good, good. Okay, so the value of a formula, as opposed to doing it the old-fashioned way, one of the great values is that we can jump ahead. We don't have to do every individual step. If I didn't have this formula and I wanted to find out what's your balance at the end of 3 years, you have to do it step by step, because you have to find out how much interest did you earn the first year. You have to get this $250. Then you have to add that $250 to the second year so that you can earn interest on that money the second year. Then you have to figure out this number, how much did you make in interest the second year, and you have to add that to your balance. So if I asked you to figure this out, you know, how much money will be remaining in your account, or what will be the balance at the end of, say, 10 years. Let's move this down. If I said, okay, let's just skip down the road here and see how much money is in your account at the end of 10 years. Well, doing it the old way, we'd have to do it step by step by step by step, because I need to figure out what is the balance at the start of the 10th year. Well, you can't figure that out until you figure out how much you earned the previous year, and so you have to know the balance on the account on the 9th year, then the 8th year, and so on. So doing it the old-fashioned way can take a really long time. It's a lot of work, and it's a lot of room for mistakes. But this great little shortcut here, this formula, helps us get to the answer fairly easily. It's just going to be 5,000 times 1.05 to the power of 10. That will tell me the balance on the account after 10 years, if it earns interest, compounded once a year at the end of the year, and the interest is given as 5% annually. Good. So now we can just type that into our calculator. Put that over here. So 1.05 to the power of 10, so 10 years earning this interest rate, 5% interest rate, times your initial balance, enter. You get $8,144.47. 81.44.48. Good. Questions? Okay, 47 of this. 81.44. Any questions at all? 47. Okay, so that's the more sort of generic version of the formula, right? So far we have that if P is the initial principal, right? P is the initial principal invested, and we know that we have this formula here where we have 1 plus the interest rate, R, given as a decimal, of course, and then raised to the number of years, T, right? So this is the general formula for it. And that's assuming that, or this works fine as long as the interest rate is in years, and this is in terms of years. Okay, but what if they're not in terms of years? Then it turns out that it's the exact same formula as long as these two things match. So like if they're giving you the interest rate per month and then they're asking you 3 months later, it's the exact same formula. They're asking you, you know, after 20 days, what's the balance on the account if you are earning interest, and then they give you a daily rate, then that's fine. If these two things match, this is the formula. If they match. If they match. Good? Okay, so if they match, this is the formula. But what if they don't match? What if one of them is given in terms of month, every month, and this one is given in terms of, you know, years? They don't match. Or this one's given in terms of days, and this one's given in terms of months. They don't match. So we have to adjust it a little bit. Luckily for us, it's not that complicated because rates are almost always given on an annual basis. It's almost unheard of to not be presented a rate that is not annualized, right? And that's just a decision that the federal government or somebody has made. I'm assuming a federal regulation, probably to make things a little easier, because otherwise I think people would be a little confused. If banks were allowed to give you rates that were not annualized, I think it would be pretty easy to confuse people. and trick them into thinking something is better when it's not. And it'd be harder as a consumer to make a good choice if the banks were allowed to give you rates at in different non-annualized forms, because it's hard to compare and contrast. It's hard to really figure out things, and most people would get tricked. They don't know that much math, right? Any rate, so interest rates are almost always given as an annual thing. So when they don't match, this will be usually given in years, and then this will be given in some other term, like they say months, for example, but this one is in years, or this one will be in days, and this one will be in years again. So what we do is we make the match. What we do is we divide the rate by a value that will give us the rate in a form that will match the time frame here. So, for example, if the time is in months, for example, if the t value is given in months, then what we have to do is take the r value, which is per year, and then divide it by the number of months in a year, right, where there are 12. So if we take the rate that's given per year, just to make it an easy number, let's say that they tell you it's 12%. Well, that's a little too obvious. Let's make it 24% per year, 24% per year, and they're asking you about something in terms of months. Well, what you got to do is you got to divide that 24% times 12, divided by 12, so you get the monthly rate. And then once you have the monthly rate, then you got to figure out, well, how many months are they asking you about? Does that make sense? Sort of, kind of, maybe. Okay. So what matters is how often this interest is going to be compounded. Does that make sense? So even if they match, even if it's given to you in years and months, I'm sorry, if the rates match, if they're telling you that the compounding happens more often than once a year, then you have to make them match and have them match the time frame in which they compound. Okay, so let's look at the formula in general, and we'll apply another example. So exponential functions occur in calculating compound interests. Okay, good. Principle. Okay, so we have, this is very similar to the example I just pulled up. So to the third power, to the kth power. Okay, so here is the general formula for compound interest for various time frames of compounding. So if n is equal to 1, it means it compounded once a year, which is the formula we just did. Right? So if n equals to 1, then the formula becomes that the interest earned on the balance on your account when p is invested becomes just this, the formula we just figured out, right? That's when n equals to 1. When n equals to 12, compounded 12 times a year, this means monthly. Right? In 1 year, it gets compounded 12 times. It means it gets compounded once a month, right? Okay, so now the rate is going to be given to you in terms of years. So in order to get the monthly rate, we take the r value and divide it by 12. And that'll give us the rate per month. Okay, so that means that this guy right here now is the rate per month, interest rate per month. Okay, because R is going to be given to you in terms of rate per year, but if you're doing compounded monthly, that means that if you take that annual rate and divide it by 12, you get the monthly rate. And now you need to figure out how many cycles of the compounding must happen. So for example, if they asked you for 3 years, let's say t equals to 3 years, but now you've changed the question to compounding per month, then that means that there's going to be 12 times 3 makes it 36 different cycles, right, where you figure out the interest earned that cycle, you put it back into the balance, and then you multiply it again. So what we need to do here is to multiply this by 12 times t. 12 times t will tell you how many months, and now these things will match, right? So t is 3 years, that means there's 36 months. If t is 2 years, that means there's 24 months. And then that way these two things will match. We'll have a monthly rate, and then we'll have a time frame that matches the this rate, monthly rate and the number of months. So this will be the formula when n is equal to 12. Good. So in general, the formula is just based on n, the number of times that that your account is going to be compounded per year. Any questions on this formula? Anybody? Anybody? Okay, here we go. Good enough for now. Okay, so a sum of $1,000 invested at an interest rate of 12% per year. Find the amount of the accounts after 3 years if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay, so the rate and the length of time invested are presented both in years, so that matches. To begin with, that matches. That's in years, and this is in years, so that first hurdle is already there. If it was a real simple question that they said compounded annually, so that first one is n equals to 1. It's compounded annually, n equals to 1. Right? This is annually. And why did it jump to such a thick thing? Annually. Okay, so then our formula says that A of t is equal to the principal times 1 plus the rate to the power of t. So for us, that's going to be equal to 1,000. Principal was $1,000. 1 plus the rate, which is turned into 0.12, to the power of 3, which is 3 years. Good. So we get an answer from that. That's going to be 1.12 to the power of 3 times 1,000. I'm getting $1,404 and say 93 cents. Good. This is A of 3. Interest after 3 years. Okay, so then the next one was semi-annually, quarterly, and then finally monthly and daily. All right, I'm not going to do them all for the interest of time, so let's just skip around to, say, the daily rate. Let's jump to the last one. Oh, let's say quarterly. Quarterly means that it happens every 3 months, 4 times a year, quarterly, right? So this is the case where n equals to 4. N equals to 4 is quarterly. And so our formula becomes this: A of t equals to the principal amount invested times 1 plus, and now it's the interest rate divided by 4. The interest rate is annualized at 12%, but if we're doing it quarterly, we divide that by 4, we get 3%. So it's 3% every 3 months will get us to 12% per year, right? To the power of, and now we have to multiply the number of times we're compounding it per year, which is 4 times per year, times the length of time t. Good. So for us, we had 3 as the value of t. So that gives us 1,000 is the principal amount invested. 1 plus, and this was 12%, 1.12 divided by 4, to the power of 4 times 3. Or A of 3 equals to 1.00, not 1, comma, 0 times 1 plus 0.03, the power of 12. Okay, so 12% compounded annually, I'm sorry, an interest rate of 12% per year for 3 years, compounded every 3 months. That can be solved by doing this. Instead of 12% per year, it's 3% per quarter, per 3 months of the year, with 12 cycles. There will be 12 cycles, 12 quarterly cycles in a 3-year time frame, right? So the compounding will happen 12 times. Good. Okay, so now we can just punch that into our calculator, and we see we get a slightly different number. So it'll be 1.03 to the power of 12 times 1,000. We get $1,425.76. Any questions? No? Okay, let's just look at a table with all the other values. Let's make sure we match for ours. Here is a table that has all of them, a nice neat thing. So for annual, n was equal to 1, right? We just replaced the n with a 1, and we end up with this, which is exactly what we had up here, $1,404.93. For quarterly, we replace the n with a 4, and we end up with exactly what we had up here, $1,425.76. Good. Say, for example, monthly, we replace the n with a 12, so that means that instead of getting 12% per year, we're getting 1% per month for 36 months. Good. Compounded monthly. $1,000 invested at 12% per year for 3 years, you're going to get the same answer as saying $1,000 invested for 3 years, compounded monthly. So you get a monthly rate of 1%. A monthly rate of 1% for 36 months is the same thing as saying a 12% annual for 3 years, compounded monthly. Good. Any questions? No? 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 Another case. A sum of $1,000 invested at an interest rate of 12% per year. Find the amounts in the account after 3 years if the interest is compounded. Wait, did I just copy? It's the same question as that one, so I don't know. It seems weird. Okay, so if an investment earns compound interest, then the annual percent yield is the simple interest rate that yields the same amount at the end of 1 year. Okay, so it's kind of like the equivalent amount. So it makes this interest rate makes it easy to compare different offers, right? So if some bank offers you an interest rate that's compounded monthly, another bank offers you a different rate that's compounded every 3 months, you know, how do you compare them? How do you know which one's better? Well, it's just simpler to figure out what would be the simple rate equivalent that would give you the same amount at the end of 1 year, and that's the annual percent yield. Good. So, for example, find the annual percent yield for an investment that earns an interest rate of 6% per year, compounded daily. So we know that our formula is going to be equal to this. It's going to be equal to the principal amount times 1 plus the rate, r, divided by n, the power of nt. Okay. So then this guy, let's put it below. This guy is going to be equal to so this guy is going to be equal to the initial investment. Come on. Times 1 plus r divided by 365. Oh, r is given to us as 6%. So this is going to be 0.06% divided by 365 days in 1 year, approximately. Not quite exactly true, right? It's like 365.25 days in a year, which is why we end up having a leap year every once in a while. I don't know if you guys knew this, but we didn't really account for that in our calendars for a long time. So we kept like falling behind over the centuries. As centuries went by, the weather would no longer match what we thought it would be, right? Summers are all of a sudden cold and winters are all of a sudden warm because we kept falling behind a quarter of a day every year, 4 days, you know, every four cycles. So over centuries we kept falling behind until we finally readjusted our calendar for it. So one day, like in the 1300s or something, we just skipped like a month in the calendar. It just like disappeared. Wait, was it in the 1300s? Forgot when it was. You can Google it. It's pretty interesting. Anyway, 365 times t. And they give us t per year compounded daily. Find the annual percent yield for an investment that earns interest at a rate of 1% compounded daily. All right, well, so let's make t equal to 1, say for 1 year. Then this guy would be equal to 1 right here. Okay. And then this is just some number we can figure out. So it's going to be p times whatever this is. So 0.06 divided by 365 gives us this tiny little number plus 1. So I'm getting, this is 1 plus 0.1230164 to the power of 365. Oh, come on. 4 to the power of 365. Good. Okay, so then we just figure out what that is. Power of 365. I get p times 1.06183111 if you want to be a little more accurate. Okay, so the principal amount multiplied by this decimal right here will be your interest at the end of 1 year. If you have 6% 6% annual compounded daily. Now, if you want to find the equivalent amount, right, an equivalent offer that's just annualized, then the formula would be really easy, right? So I'll put it over here. If n was just equal to 1, compounded annually, then the formula would have been really easy. It would have just been p times 1 plus r raised to the power of t. So at the end of 1 year, t is 1. This would have been p times 1 plus r to the power of t, right? Where this r is the annualized rate. That's equivalent to this. Compounded once at the end of the year. Okay, so we match these up. So t is equal to 1, since we're just letting t equal to 1 year to compare these two. That's just a 1. So when we set these two things equal to each other and solve for r, this is going to be p1 plus r. Then we divide both sides by p. Divide this side by p. Divide this side by p. Both the p's cancel. And we're just left with this 1.06. Come on. I think this file is too big now. 1.06183 equals 1 plus r. So if we subtract 1 from both sides, we get this 0.06183 equals to r. So there's our answer. 6.183% is the equivalent rate, annualized rate. This is per year, compounded annually. Compounded annually, that would give us the equivalent amount.